Hello, and welcome back to this free training series on FEMA P-154, Rapid Visual Screening of Buildings for Potential Seismic Hazards. This is Module 3, Rapid Visual Screening, Procedure Part 1. You're watching the third of 9 training videos outlined here. Module 1 was an introduction to FEMA P-154. Module 2 went over earthquake hazard and seismic performance of buildings. Module 3, this module, will go through the rapid visual screening procedure, giving an overview and walking through pre-field planning tasks. Looking ahead, Module 4 will continue going through the rapid visual screening procedure, focusing on field screening. Module 5 will go through key building performance indicators. 6 and 7 will go through FEMA building types. 8 will be a class exercise, and 9 will be some concluding remarks. With that, Mike, please take us away.
So Module 3, we're going to go through the actual RVS procedure. We'll give you a brief overview. We'll look at the data collection form. We'll look at the pre-field planning tasks. There's actually 3 primary areas that the RVS procedure targets, and that's first is pre-field planning, and then we have the field surveys, and then we have the last one, which is we have all this data, what do we do with it? And that's our documentation area. So we're going to discuss pre-field planning tasks in this module, and that includes determining our seismicity for our building site. That's important because we have 5 forms that we have to select which one is appropriate for our site, which is all a function of the seismicity of our site. Then we're going to briefly talk about seismic code adoption dates. That factors into our modifiers when we get into scoring, as well as benchmark years, establishing those for our building. We'll talk about cutoff score because we will get a numerical score for the RVS procedure for our building. And that's ideal because we can then begin to look at those scores in terms of prioritization for our risk to our buildings. We'll talk about soil type. That's also a key important aspect that Sarah talked about in the previous module in terms of building excitation. And then we'll look at some examples of where might we collect some of this pre-field planning items that we're going through. So an overview of the RVS procedure. Here's the 3 areas I spoke about. Pre-field planning is one. The second one is the field screening, and the third is post-field trip, or we have all this data, what do we do with the documentation? So pre-field planning, we're going to define our project. What personnel are we going to utilize to train to be our screeners, our supervising engineer. We're going to look at defining our seismicity region to select our form, look at code adoption dates and soil data. Field screening, which will be in the next module, we'll be looking at our FEMA building type, our basic scores in a general sense, our score modifiers, how to calculate our level 1 score, what is level 2 screening if it's selected to be performed, and then a little bit more about the forms and the post-field trip data. Database entries also will be discussed in the next module. So we're going to focus our attention on the pre-field planning in this one for the procedure. Data collection forms. Here's an illustration of the data collection form utilized. Now, the first item you'll notice, this is a 1-page form, and there's 5 of them, representing the 5 seismic hazard regions that the RVS has been broken into. Up in the upper right-hand corner of our form is where we define our seismicity level. And what's shown here is it's a level 1 form, the front of our form, and it's a high seismicity in this case. And so there's distinct areas within the data collection form that we're going to be defining here. So the next section, which is pretty much the upper half of the form, is what we call building information. And that's just collecting a bunch of information on the building itself, the address, the latitude and longitude for the building, our ground motion parameters, which we're going to talk about here shortly, who's the screener, who actually did the review, date and time when they did it, information on number of stories, what code was involved in the design if we can determine that, were there any additions, when were the additions done. We can record information about the occupancy, the soil type, And then we can also then begin to look at recording some of our modifiers that we score down below and giving us more definition. So that's our upper half of the form. Just below half, roughly half of the form, is where we start the scoring for the RVS procedure. And so that section defines our 17 building types, as well as what the basic score is relative to that building type, relative to the strength or the seismicity associated with the form that we're using. So in this case, it's high seismicity. So all of our basic scores under each of our building types, 17, are related to shaking that particular building type as if it was in a high seismicity, the strength of that shaking. And so that's the calculated or average collapse potential for that building type given a high seismicity region. So the other 4 seismicity regions or data collection forms are going to have a different basic score than what we see here. And that's all a function of how strongly we're shaking the building. The next section below the basic score is our score modifier section. So the basic score is our average performance for that particular building type. And then what we do is, based on our field screening, is we look at the building for unique characteristics associated with that building. Those are our modifiers to adjust that score to come up with our final score, level 1 score. And that's our score modifier section. Now, the bottom of our form is our evaluation summary. It's just a summary of what we've done to date, and it records other things such as the extent of our review. Did we go inside the building? Did we have structural drawings that were available for us to review? What source did we use for our geological data? Did we speak with anybody when we were out there reviewing the building in person? And so that information can be recorded. There's also an appropriate area where did we do a level 2 screen? The first part of our form here is a level 1 screen, but we can take a design professional familiar with seismic design and retrofit and have them do a level 2 score, which is essentially, I call it the back of the form or second page of the form. Well, there's a summary for the information from the scoring for the level 2 review on the front, and that's in the lower left-hand corner of our form here. In the middle of our review summary section is a box called Other Hazards. Now, other hazards are associated with elements of the building, but they're not scored. They're important, so that's why we capture them. And so, but this is an area where we can capture those elements, but we're actually not scoring them. A good example is any geological issue that we find with our building. Liquefaction was discussed in the previous module. If we have associated liquefaction potential for our site, we can identify it and note it here. So we don't score it, but we capture it. And so we can actually recognize that we have a potential liquefaction hazard, even though our building might score very well. So that's other hazards. Then in the far right box is kind of the overall summary, and that is identifying actions required. Is our building meet our cutoff score? So it's good, or does it not? We could have buildings that don't fit one of the 17 building types represented within our scoring. That's completely possible. And so we have a box to check for that regard. And then the basic summary out of action required is, do I need to perform further evaluation for my building? That's the outcome of the action required box. And there's both box or areas for recording the building summary and then also for non-structural components. If we take a little closer look at our scoring block, which includes our 17 building types and our basic score along with the modifiers for our level 1 screen, we can see that we've got the 17 building types at the top. And those are from 4 material types. So we've got wood, we've got steel, concrete, masonry, and then we've got MH or manufactured housing. We're going to talk more about these in module 6 and 7 when we go through the specific 17 building types. So we have our basic score, our building type, then we have our basic score associated with each of those. And I believe this is from the high seismicity form. So that's what these basic scores represent. Strong shaking in a high seismic environment. And then we have a close-up here of the modifiers associated with our high seismicity form below that. The next row or line is called minimum score, or SMIN. This is the minimum score for each building type in a high seismic environment, in this case, to where if we can't possibly get a score lower than SMIN, or the minimum score. And I always like to call this the all sins score. If I have everything bad, which is up in my modifiers for any particular building type, I just can't get any lower score than this. And these have been analytically calculated to reflect this. And so this is SMIN. If we calculate a score less than SMIN, we use SMIN as our final level 1 score. And we'll talk more about this later. So if we look at just a quick example of how the RVS procedure works, here's an illustration for our basic score and our modifier block again. And the example they're showing or illustrating here is for a W1 structure or FEMA building type. And W1 stands for residential or light wood frame home, our homes. And so what we see here is it's arranged in a column in terms of the scoring, our basic score, and then our modifiers below that. So for a wood 1, W1, we have a basic score of 3.6. That's our basic score. Now, our modifiers, which are below that, is what we evaluate our building for those specific characteristics. And if we have them, then we have to select the score value underneath that modifier. And so what the example here is telling us, it says, okay, we have a basic score of 3.6. We have a moderate vertical irregularity, which is minus 0.7. And what you'll find is, as we talk more about irregularities a little bit later in other modules, that most of the modifiers are negative, which means they represent bad characteristics for good seismic performance to our built environment. And so generally, most of them are all negative. And so we have a moderate vertical irregularity. They don't share with us what that is, but it's a vertical irregularity, minus 0.7. They are telling us that we are on a soil type A or B. Now, the basic scores are calculated based on a type CD soil, which is pretty average across the United States. So if we have a soil type under our building other than a type CD soil, we have to modify our score. And so a soil type AB signifies that we have very good soils underneath our building, bedrock, essentially. And so that's a plus. And so we have a modifier of 0.1, plus 0.1. Now, our final score and how we arrive at that is we take all of the scores above. So in our example, we'll take the basic score plus the moderate vertical irregularity plus the soil type modifier, add them all up algebraically to come up with a final score. Very straightforward. So 3.6 minus a minus 0.7, plus 0.1 gives us a final score of 3. And that is our final level 1 score. Now, our minimum score for a W1 building in a high seismic region is 1.1. So our final score of 3.0 is greater than 3.1, so we would use 3.0 for our final level 1 score in this particular example. We'll see more of these as we move through the other modules. Pre-field planning tasks. So this is an area where before you go to the field on the field screening to do the visual review, you want to try to acquire as much information as you can on the building, which helps you actually review it in the field in most cases. The first part, though, is we need to determine the seismicity where our building resides, and that is so we can select the appropriate form of the 5. Then we'll look at code adoption dates. We'll talk about the cutoff score. What does the scores mean? What's a good score? What's a bad score, etc. And then we'll look at other pre-field information associated with our building. What type of structural system do we have? Do we know the vintage, occupancy, soil type, geological hazards? And so there's sources of information that we can tap into to provide this information ahead of time. The first element is to look at what seismicity region our building resides in. There's 2 ways to do this. In Appendix A of the P-154 document is a series of color-coded maps. Of the 5 seismicity regions, from low, moderate, moderately high, high, and very high, so 5, they have provided us with a map of the US, Alaska, Hawaii, Puerto Rico, and Guam, of the counties associated with each of those areas of the states or territories, that's color-coded with the appropriate seismicity for that county. So it's easy just to go ahead and look at the maps and say, okay, that's my county where my building is, and then compare the color to the seismicity, and you pull that up. That's one way to do it. Now, there are some additional maps. The current one here is showing the entire United States, so the county boundary lines are pretty small. There are just multi-state regional maps that blow up the US, so you can look at those. And so this is an illustration showing some of those close-up maps in the 5 seismicity regions. And again, as Sarah mentioned in the last module, these are based on the 2008 USGS seismic hazard maps for the maximum considered earthquake ground motion. They are also based on a site soil type B. Okay, that's important, which we'll see here shortly. Seismicity is then calculated from these county maps based on the highest shaking in a county. And so a potential problem here is if you are in a state where you've got counties that are geographically very large, you could be overestimating the seismic risk through a 154 screening because the maps are based on the highest shaking within the county. And so that's why I prefer to look at the second method, which is going directly to getting the ground motion values and then comparing them to the table within the P-154 document to see where we land in terms of the actual seismicity and thereby the form. And so here's another example of Alaska, and it's composed of only 3 colors: very high seismicity, or moderately high seismicity. You can't get low in Alaska or moderate, unfortunately. The second way is, and this is in the P-154 document on page 2-16, what it's going to refer you to is go to the USGS webpage for design ground motions. And when the P-154 document 3rd edition was created, those ground motion values could be accessed directly from the USGS website. They had them there. However, USGS now does not maintain in a manner that you can pull these values anymore. So they have 3 resources by which you can link to pull these values. The first one is called the ASCE7 hazard tool, which is the one we recommend because we believe it's going to be there long term. So that's the one we're going to use. And so if you click on that link from the USGS website, you'll come up with a map of the United States that says ASC7 hazard tool and a box up in the upper left that provides some entry information that they are requiring. So we can either enter our address for our building, or we can select lat long, or it's an interactive map, so you can actually find it on the map, zoom in and find your building. I don't think I've ever used that. I always use lat long. So if you input your lat long and then click the search button, what it will pull up then is the ground motion values, or I'm sorry, another screen that shows where the building is relative to your address or the lat long, and it pulls up another information box that it requires some more information. The first box is going to be what they call, it's a pull down menu. So they ask for information about the standard or code that you want ground motion values to be pulled from. In this case, select the ASCE 716, and then below that is another pull down box area or pull down that asks for the risk category. And though that varies from 1, 2, 3, or 4, just select 2. It has no bearing on the actual ground motion values that we're going to get back. But the next box on the to the right is site soil class, and that's a pull down menu again. What we want to do is select site class B for rock. That's the one we want to select. Now this will affect the ground motion value, so make sure that you select B. And then down at the bottom it asks, there's a section called load types. What we want to do is click on or select the seismic load type down there, and then push view results. And once you do that, you'll get a box that comes up. You can select report summary, and then the 2 values that we want are the 2 at the very top, which is S sub S and S sub 1. And so when you do that, you're going to see that our values in this example are 1.5 for S sub S, which represents our short period. We call it the short period, or the 0.2 second ground motion response. And then S1, which we call our long period, which is our 1 second, and that's 0.676. So those 2 values are what we need from this source. So if we pull those 2 values and then enter into our table that's out of our P-154 document, which is on page 2-16, and that table defines our 5 regions of seismicity, so from low to very high, and then our breakout between our S sub S, or short period ground motion level, for each of our 5 seismicity regions. And then also it breaks out the ground motion region for S1, our long period ground motion type. And so there's a range. For instance, for low seismicity, it says if our S sub S value is less than 0.25, then we are in the low seismicity region. We also have to have our S1 value less than 0.10. If both of those conditions are true, then we have low seismicity. We pull the low seismic or low data collection form, and that's the one we use for our building. And so the other regions are broken out similarly, roughly about 0.25 G relative on the S sub S, and 0.1, 0.2 G for S sub 1 in terms of the breakout. So if we take our 2 values that we found, 1.5 and 0.676, and compare them to our table, what we'll find is that our 1.5 sits right at the break point between high seismicity and very high. And so to be in very high for S sub S, it's 1.5 G equal to or greater than puts us into the very high category. S sub 1 we have to compare as well, and that's 0.676. So the break point between high and very high on S1 is values greater than or equal to 0.60. So we're 0.676. So we are greater than that, and therefore we are in the very high region. So you can tell though, with this particular example, we are right on the break from a high seismicity to a very high seismicity. And this is the region, this is why I like to use this method versus the hazard maps, because it provides key information on exactly what the shaking is at my building site, and it provides some relative measure as to where on the breaks between the seismicity regions that I'm going to be at. If I'm close to one, I might seriously consider pulling the documentation form for that close or that adjacent seismicity region and score the building both ways to kind of see what the difference is between the two scores. Because the basic scores are calculated based on the median of the scores within each region. So you can be off by as much as, I mean, for S sub S, the moderately high region is from 0.5 G to 1 G. That's half a G. That's a lot. And then if you go from on the high seismicity, the region is defined from 1 G to 1.5 G. So that's why I like to kind of use this and look to see whether I'm right at a transition to the next seismicity region or not. And it gives me a little more information. So for us though, we're clearly in the very high. We're close to the breakover point, but we're very high. So that would be the data collection form that we would pull for this particular building based on our seismicity, which would be very high. This one happens to be in Anchorage, Alaska, and is reflective of our class exercise, which is in module 8. So this is associated with that. So we have very high seismicity. Code adoption dates. This is an area where two of our modifiers, I should say, are associated with code adoption dates. The basic scores as calculated, I mentioned, are calculated on a type CD soil. They also are reflective of an average level of seismic design attention that should have been incorporated into the buildings as if they were designed roughly in the early or mid 1990s. So essentially our seismic design provisions at that time for buildings designed for that should be very reflective of the basic scores calculated that are reflected on our forms. Okay, so that's the middle. Now, what do we do for old buildings? That's our pre-code, what we call our pre-code modifier. And so if we have older buildings, very likely seismic design was not incorporated into the original design and construction. And so they're not reflective of our basic score. And so we modify our basic score because of that. So that's below our average. Now, the other side of it is, okay, hey, we have buildings that have been designed to the, 2, 3, 5 years ago to the latest building code, IBC, and the seismic provisions incorporated therein. They should have a better performance than this average level of building design of the 1990s. And sure enough, they do. And so if we have that condition, we can modify our score to account for it. Those two, whether we have pre-code, old building, or benchmark, new building, is where we need to establish our code adoption dates. That's the importance behind this. And so our year of construction and design for our building becomes very important for establishing this. And even more so is it becomes challenging because sometimes a jurisdiction hasn't adopted seismic provisions in their code until very late. For instance, there are some jurisdictions that never started enforcing seismic design of buildings until early 2000s. And so you have a condition here where it's not reflective of 1990s seismic design because it likely wasn't done. And therefore a pre-code modifier should be taken in that instance. And so that's the challenge with code adoption dates and trying to find that. We'll talk about how to achieve that or obtain that information to help us out there. If we look at the pre-code years, the P-154 document provides us some guidance in how to determine that once we know the vintage of our buildings. Like I mentioned, it does vary by region and jurisdiction, enforcement for seismic provisions. And so the local jurisdiction's building department are great resources to talk to figure out when they began to first adopt and enforce the seismic provisions. Design professionals, particularly those old grizzled ones, are great to tap into and talk to them about, hey, when did you start doing seismic design here in this region? If you can tap into that resource as well. If you are on the West Coast, which utilizes the Uniform Building Code, adoption and enforcement was much more rigorous for seismic design than the central and eastern US. They suggest if you have a building that's older than 1941, then you should consider it pre-code, no seismic design attention, and take the pre-code modifier. If you're in other areas, it could be as late as the 1990s, early 2000s. Again, that's going to be a function of the local jurisdiction and their enforcement of seismic design. So that varies. For benchmark years, so that's our newer buildings. So where are those breaks with our building types and our code? That's again are going to be a function of our region and jurisdiction, our FEMA building type. So which building type are we talking about? And then also, what was the governing code when our building was designed? Was it the IBC, International Building Code, which is our current code now, or one of the three model building codes used in the past? Uniform Building Code, the Standard Building Code, or the National Building Code, BOCA. P-154 document provides some guidance for us in that regard, in that it provides a table for all of the 17 building types with the building codes reflected at the top that it was designed under. Was it designed to BOCA or the Standard Building Code? That's one column. And the second column is, was it designed under the UBC or Uniform Building Code? Or was it designed under the IBC or International Building Code? So the table reflects the 17 building types and then a date associated with each of the building codes for that building type. Some of them have not applicable, which means if you're designed, for instance, PC2, precast concrete frames, if you have a building that is been designed under the BOCA or Standard Building Code when the time it was constructed, then post benchmark years are not applicable. It says it doesn't matter what year you were, if it was designed to the BOCA code, it doesn't apply. You don't have post benchmark. So you should just use the basic score for that particular building type in that instance. So all 17 building types are reflected within this table. And the key point to remember about this is if we look at one table here, which reflects steel moment frames. And the dates in the table are defined generally by a major change that was incorporated into the building code at the time. Whatever building code it was, but something happened, lessons learned, that caused a change in the seismic design provisions in the code. A good example is steel moment frames. And in the table here, it shows that if we were designed under BOCA or Standard Building Code, which means Central US or Southern portion of the United States, it says not applicable. There is no benchmark year for steel moment frame buildings. If you are designed under the UBC, which is West Coast generally, then the benchmark year is 1994 under the UBC. Well, why is it 1994? In 1994, the Northridge earthquake occurred in Southern California, and it caused a significant change in the seismic design provisions for steel moment frame buildings due to the damage that was experienced there. That resulted in pretty significant changes for steel moment frame design in moderate and high seismic regions. And therefore, that's why this is a break point or benchmark year for steel moment frames, to where if you are designed to the UBC after 1994, then you're designed to these much better or higher seismic design provision for steel moment frames. So that's the idea behind the benchmark years. And just to fill it out, if you're in the IBC, it's 2000, which is the first year the IBC came out. You would have designed to these higher provisions, seismic provisions. Therefore, you're post benchmark. You're better than the basic score, and that's what's reflective in these tables. The cutoff score. Let's talk about that. You will get a numerical score, level 1 score for your building, which is fantastic because now we can begin to prioritize the risk associated with multiple buildings. The score is reflective of the probability of collapse under the MCE shaking, our seismic hazard region of one of the 5, that our basic score was calculated and then we modified. So if you have a score or a final RVS level 1 score of 2, that says that you have a 1% chance of collapse in your building, which is a probability of 1 in 100. That is generally considered acceptable risk and reflective for life safety within our building codes. So that's a table reflective here. If we have a final RVS score of 1, that means we have a 10% probability of collapse, or 1 in 10. So it says if we have 10 buildings, let's say we have W1, our wood frame homes, we have 10 of those buildings and we shake it to the high seismicity region and we have a score of 1, that means out of all of those 10 buildings, one of those buildings is likely to collapse. 1 in 10 or 10% probability. So that's what the scores mean. Now, if we have an important building, like a hospital, well, life safety, 1% probability of collapse with a score of 2 is probably not what we want to have as a cutoff score. We might want to consider looking at a higher level score, higher number. And so one suggestion is 3. If you have a final RVS score of 3, that reflects a 0.1% or 1 in 1,000, given that level of ground shaking or seismicity our building is in. And so that's the cutoff score. Again, for normal buildings, generally the cutoff score is considered as 2. And if you have a more important building, then a higher number is looked upon, and that generally is 3. So again, recommended cutoff score is 2. For most buildings, standard occupancy, that is appropriate. For critical facilities, we tend to look to a higher score, i.e. 3, for that in terms of how we want to screen buildings. So if our final score is, say, 2.5 and we're looking at a cutoff score of 3, then we're going to say, well, this doesn't quite meet my performance objective. Then I want to perform further evaluation for my building because it doesn't meet my cutoff score. Same thing with 2. If I had a 1.5 and I had a 2, doesn't meet my performance criteria cutoff score. I want to give it to a design professional for further evaluation to look at the building further for seismic risk. Soil type, we saw that in the last module in terms of its importance and how it's reflected in our basic scores. And so we want to understand what soil type is beneath our building. And there are several sources for that as well, but we want to make sure that remember our basic scores are calculated based on a type CV soil, and we modify that score if we're on a better soil, AB, or if we're on a type E soil, which is a poor soil. And then that's going to be reflective also of our building height. So there's two parameters there that we have to consider. We can't just go out to the field and look at the soil and say, that's a type D soil. Can't do that. We need some more information. The best sources for obtaining soil type is if we're able to pull the construction drawings for the building under design. Oftentimes the structural engineer will have identified the soil type that was used in design, and so we have it right there. If we're able to pull or obtain the geotechnical investigation report for the site, that's going to have the soil type identified as well. And so those are great sources there if we can get them. There's also, if you're in a larger urban area, there are urban hazard maps that have been developed. And in order to develop the hazard maps, they have to develop or understand what the soils are. So there's generally regional soil maps that you can pull. The Bay Area has them. I know in the Midwest here where I'm from, St. Louis has them. So they're a great resource. Oftentimes you can find that information on the USGS website. The USGS website also has soils information for the entire United States, what they call their VS30 database. And if you can access that, you can pull that information out. If we have the soil type and we have the geotechnical report, we can pull that information and compare it to the table that's within the P-154 document. And that's from the geotechnical investigation report based on whether we have a shear wave velocity for the site. Do we have blow counts from the geotechnical report? Do we have the undrained shear strength tests that have been performed? If we have that information, we can pull that, compare it to what's in the table here, and find out what our particular soil type is underneath our building. Again, the most common types are our CD soils, which is reflective of our basic score again. But if we have something outside of that, we have to modify our scores, and that's where we get into this a little more involved process of determining exactly what our soil is if we can pull these parameters up. Regional maps. So here's a figure of the Bay Area showing municipalities outlined, and then they're color coded based on the soil type. So it's pretty easily to look at this map where your building is at, and then to pull out the relative soil type, whether it's an A, B, C, D, or E, and then utilize that information for determining soil type and whether or not we need to modify the basic score for a better soil or a soil that's not quite as good, type E. Pre-field data collection sources for obtaining information about our building. There's quite a few sources. There's the assessor files that, again, it's going to be jurisdictionally dependent in terms of how much information is there and recorded, but that can provide some information about your building. It certainly can provide vintage, which is one of the key parameters we'd like to have for code adoption dates. There's building department files. If it's a pretty robust building department, maybe they'll have them electronically and searchable, and they might have the construction drawings for the building. Particularly for maybe newer buildings, they're electronically filed, and so maybe we can pull them up in that regard. So building department files are great resources to tap into. There's also municipal databases that can be looked at. One of those is Sanborn maps or insurance maps. If you're in a metropolitan area where you have older construction, the Sanborn maps can actually be very helpful in providing basic information. And in fact, I thought Sanborn maps originally were for large urban areas, but in fact, they're Sanborn maps for smaller municipalities. Now, I mean small rural towns. So it pays to Google Sanborn maps for whatever city your building happens to reside in. Another source is also previous studies, which is a little bit difficult to try to dig into and find those, but if they are there, you might find that there's been a previous seismic study done for your building or buildings that you're interested in reviewing. And then the construction documents are actually last on the list here, but they're probably one of the most important ones, but they are oftentimes difficult, particularly for older buildings. And so the photograph here shows an excerpt from a building department file that has a lot of information associated with a particular building, including its address, square footage, land use, etc. So you can pull out some information that's useful with regard to establishing our vintage for the building, particularly. So let's have a quiz for our for this module. So true or false, a higher score indicates a more hazardous building. True or false? And go ahead and pause your video here, and we'll give you a few minutes to think about that, and then you can come back and tell us what you think it might be. So Gigi, what do you think?
I think that it's false, that this is not true.
It's false. That's correct. Remember, a higher score reflects a lower probability of collapse, which means a lower risk. And so we talked about these critical facilities considering a cutoff score of 3. That's higher than a standard cutoff score of 2 for most buildings. So that is false. Okay, time for a question. Any questions out there?
All right, thanks, Mike. Can you elaborate on the use of either the seismicity maps in Appendix A or versus obtaining the ground motion values from the ASC 7 hazard tool to determine which data collection form to use?
I prefer to use the second method, which is to obtain the actual ground motion estimates directly from the USGS website or the ASC 7 tool. It provides me more information to understand where it falls relative to the actual 5 seismicity regions. Am I close to a boundary to where I could be shaking the building higher or potentially lower? And once I have information about the building, it is so easy to score the building once I have the information. So having 2 forms is really nothing. And so I think it gives a reviewer a lot more information in terms of risk potential for the building if I understand where it falls within the breakouts between the different categories. The 0.5G separation on S sub S is quite a large ground motion difference for shaking a building. And so I feel a little more confident if I understand if I'm close to a break point or not. So I prefer that method over using the actual county color-coded maps that's within the Appendix A of the P-154 document.
Great, thank you. All right, how does the soil type affect the RVS score?
How does the soil type affect? Well, remember our basic scores are based on a type CD soil. So given our 5 seismicity regions, each of the building types are calculated for their performance as if they're sitting on a type CD soil. So if we're sitting on a better soil like bedrock, our building performance is going to be better. And so we want to modify that basic score because it's sitting on CD soil, calculated based on as if it's sitting on CD soil. to reflect that improvement in our building performance. Conversely, if we are on poor soil than CD, i.e. type E soil, we want to make sure we capture that, because that's going to introduce a higher level of risk in our building due to seismic shaking, and we will make sure we capture that as well. So soil is a very important parameter to consider within all of this. It also is in structural engineering design for buildings. Within the code, the building soil or the soils have to be characterized to 100 feet in order to establish what the soil parameter is for use in design. So it's a very, very important parameter for us to consider.
Great, thanks. Okay. How does one find information related to establishing pre-code year as well as benchmark year for a building?
Sarah, you want to take that?
Sure. So there's the table in FEMA P-154 that Mike showed us that has some guidelines. But if you recall, in module 1, I believe it was, Mike talked about the supervising engineer role. And that supervising engineer should be a local engineer. And the best way to determine pre-code and post-benchmark years is to really do it on a local level with an understanding of what codes were adopted and enforced at what times for what building types. And so the best way to really accurately determine what is pre-code and post-benchmark for a given community is to engage a local engineer with knowledge of the local building code.
All right, so in the next module, module 4, Sarah will continue to go through the rapid visual screening procedure, focusing on field screening, completing data collection forms, level 2 screening, and the post-field summary. This concludes training module 3, rapid visual screening procedure part 1. We will see you in the next one.